In this section, we're going to look at epoxides and followed by the reactions of epoxides. So an epoxide is similar to an ether, but the oxygen is being shared by two carbons in this three-membered ring type structure. And at the beginning, we're going to look at some reactions to form epoxides, some of which you may have seen before. So if we take ethylene, CH2 double bond CH2, and we treat it in the presence of oxygen with silver 1 or just silver oxide at 300 degrees C, we can make this epoxide right here. So we can add that oxygen bond between those two carbons. There are some other ways to prepare epoxides, and one of them is to use a peroxide. So I'm going to painfully try to draw a 7-membered ring here. All right, so we have a 7-membered ring with a double bond. If we add M-chloroperoxybenzoic acid, so M-chloro, so put the Cl here, C double bond O, bond O. If I were to put an H there, this would be M-chlorobenzoic acid, but in this case, it's a peroxy, so we have this oxygen-oxygen bond, which is relatively unstable, and able to make an epoxide out of this 7-membered ring. Something like that. So my ability to draw a 7-membered ring is not the best. So here we have an epoxidation as well. A final method that is presented is to take something like this. So here we have an OH group here sticking off the ring and a Cl group here. So we have trans 2-chloro cyclohexanol. All right, so we have a trans 2-chloro cyclohexanol. It'd be better if that were on the screen here, so I'm just going to move that up. And if we add to this a base in water, NaOH and H2O, we can form a 6-membered ring with an epoxide. So there are 3 different methods, similar types of methods, but that are able to form epoxides. I'm not going to go into the mechanisms of these reactions, and you may have seen some of these in the past in previous chapters. But here, what we want to talk about a lot more is the reactions of these epoxides, which is technically the next section, but because this section is so short, I'm going to combine them together. So let's look at what we can do with these epoxides. So let's take the one that we just made before, cyclohexanol ring with an epoxide. We can open this thing up. If we add water and acid, okay, we can cause this to open and make a diol. So we get an OH on this side and an OH on this side. And this will be trans 1,2-diol. All right. I'm not going to be super picky about the stereochemistry here of these rings, but if we add an acid, we can open up this epoxide. Well, how does this work? So remember back to our alcohol chemistry, when we are trying to react acids with oxygen-containing compounds, okay, we are going to protonate this oxygen. And we saw this also in ether chemistry. So protonating this oxygen is the first step. So this oxygen grabs a proton. And what we end up with is this protonated epoxide here with a plus charge on oxygen. Now, something has to come in and kick this bond out. And in this case, what's going to come in and kick this bond out is water. So water comes in here and kicks this out, all right? Just like a substitution reaction, going on here. And what we end up with is the ring with the OH here. And because this is a backside attack, you end up with this on the opposite side, and you end up with the trans molecule. You end up with OH2 plus here. Now, when this happens, this proton is very acidic. So let me draw this a little bit so it's a little bit easier to see. We have these two OHs here. Well, if we have another water molecule, it can grab one of these H's. Those electrons can go there. And finally, what we end up with is the product as shown above. So, take-home message here. If we add acid and water to the epoxide, we can open this up and make a diol. This mechanism starts with the protonation of oxygen. We then have attack by a nucleophile. In this case, our nucleophile is water, and then we have to deprotonate the water to make the diol, or said another way, the protonated alcohol here is very acidic, so even a weak base like water can pull off that proton. So this is the opening of an epoxide. So if we look at some other examples, we could also add different types of nucleophiles. So this is extremely similar, and in fact it's so similar I'm not going to show the mechanism, but let's imagine that we have this same epoxide, but this time instead of adding water and H3O plus, okay, possibly sulfuric acid or something where the counterion is in a good nucleophile, we could have HX in ether. Well, what's going to happen here? Same thing. We're going to protonate here. But in this case, what's going to attack? What's going to attack is not water. It's going to be the X minus. So instead of getting a diol, what we end up with is getting the OH here as this breaks. But in this case, what kicked it out, it's not X minus anymore. It's just X, okay? So this time you protonate here, and then X minus comes in. So we get the halogen at the 2 position instead of the diol. Now, when you have a reaction like this, which is asymmetric, right? In the other case, we got an OH here and an OH here, so it didn't really matter which was which. But in this case, we have an OH on one side and an X on the other. So what we want to consider is, well, which side is going to get the OH and which side is going to get the X? So let's take an example here, and we'll pick a more simple example, where we have a CH3, bond C, bond O, bond H, bond C, bond H, bond H. So we have this epoxide here. Now, what's the difference between this carbon and this carbon? Well, this carbon is bonded to 2 carbons, so it's secondary, and this carbon's only bonded to 1 carbon, so it is primary. That is the difference between these. So if we add HCl and ether, remember before, one side gets the OH and one side gets the X, like this. Well, which side is which? Here it didn't matter, right? Because both sides are essentially the same. But here it does matter. So let's take a look at what's going to happen. Well, it turns out that we get CH3, bond C, bond OH, bond C, bond H, bond H, bond Cl, bond H. Okay, and notice, because this all has all single bonds, there's no stereochemistry here in terms of cis and trans. So in this case, what happened? Well, the OH ended up on the secondary carbon and the Cl ended up on the primary carbon. But it turns out we can also make the other product, which is CH3 bond C bond Cl, where the Cl ends up on the secondary carbon, bond H, bond C, bond OH, bond H, bond H. So in this case, the Cl ended up on the secondary carbon and the OH ended up on the primary carbon. So what we want to think about is, what is the relationship between these two things? Well, it turns out that in this case, you have 90% of the Cl ending up on the primary carbon and only 10% where the Cl is ending up on the secondary carbon. Well, what is a possible explanation for this? Well, the possible explanation for this is going through an SN2-like mechanism. And when it's in an SN2-like mechanism, the nucleophile can more easily attack the primary carbocation. It's less sterically hindered than the secondary carbon here. So steric hindrance would be a good explanation for this. But let's look at another example. Let's go to a different extreme. Let's look at C bond CH3 bond CH3 bond O bond C bond H bond H. So what's the difference between this and this? Well, this carbon is bonded to 1, 2, 3 other carbons. So this carbon is tertiary. This carbon here is primary. So if I add HCl, and ether, what am I going to get? Well, when I add this, I can get two potential products. So in this case, we have the OH sticking around here. On the tertiary carbon, bonded to the CHHCl. All right, so exactly the same as this one. In this case, the OH ended up here, and the C got the Cl. Said another way, the primary carbon got the chlorine, and the tertiary carbon kept the O. Well, I can get some of the other product, maybe. CH3, bond C, bond Cl, bond CH3, bond C, bond OH, bond H, bond H. Okay, so now I have this structure. So it turns out when I do this, I get 40% this product where the OH is attached to the tertiary carbon, and 60% this product where the Cl is actually attached to the tertiary carbon. Now, it's not quite as clean as 90-10, but at the same time, you notice we get the opposite effect. So here we overwhelmingly had the chlorine attack the primary carbon. But here we actually had a slight majority of the chlorine attacking the tertiary carbon. So what is going on here? Well, when would the tertiary carbon be favored? And I kind of gave it away there. When a carbocation intermediate is expected. And so what this tells us is that this reaction is somewhere between SN1 and SN2, because we don't get only the tertiary one. If a carbocation was favored, the carbocation would be favored on this carbon and not this carbon, and you would expect this to be, 99%. But it's not, it's only 60%. And this one's 40%, which looks like more of an SN2 type mechanism, so this less sterically hindered one is getting attacked more readily. So it's somewhere in between. Now, it's very difficult to draw somewhere in between, but your book has kind of done this here in this example. So here, you can see on this tertiary example, okay, the plus charge is somewhat here, and the bromide is coming in, and the major product is this one. Okay, but if we look at this less sterically hindered carbon here, so this one's only secondary because it does have an H attached to it. When this bromide is coming in and kicking this out, this one's actually not formed. So if you have a choice between a tertiary carbocation and a secondary carbocation, you actually don't even form the product where the OH is on the tertiary carbon. You only form the product where the bromine is on the tertiary carbon. In our example, okay, our choices were between a primary and a tertiary, and we get a mixture of both, saying that this mechanism is somewhere between SN1 and SN2. So in the next step, what we want to look at is some other ways that we can use to open these epoxides. So this is a bit complex and something to practice with, and not something that you super need to memorize. But the idea here is how scientists are trying to understand the mechanisms by doing different reactions and getting somewhat strange results, because this one clearly is pointing to an SN2 mechanism, okay, being favored, and this one, it's somewhere in between. And then if you combine this with the secondary versus the tertiary example, and not forming any of the product where the OH is on the tertiary carbon when there's a secondary carbon competing, then that one goes through more of an SN1 mechanism. So again, the mechanism is somewhere in between. So let's look at this example here where we do the opposite. So in the previous cases, we're adding acids to open up these rings. But it turns out we can also add bases, all right? So here I'm not going to get into the, if it's primary, secondary, or tertiary as much, because we already talked about that. So I'm just going to pick a generic example here where we just compare something that's like this. If we add OH minus and water, and we heat this up, we can actually do the exact same thing as if we add an acid. So we can get OH, like this. So remember, when we added acid and water, we got the diol. If we add base and water, we also get the diol. So in this case, what we need to be aware of is how this is going. Well, if you remember in the acid case, the acid would first protonate and then the water would attack. Well, in the case of the base, we have a good nucleophile here, so better than water, so it just goes the opposite way. So let's take an example here. If we have this bonded to an O, like so, and we attack with OH minus, this comes in here, and this bond breaks. And what we end up intermediately is a C with an O minus, because this bond is broken, and a C bonded to two things with an OH. Then we have H2O present. This is a strong base, it grabs that. And what we end up with is C with an OH bonded to C with an OH. So we end up with the diol in this case. So the mechanism for the acid and the base are different, but the end result actually is exactly the same. They just get there in different ways. Well, what we've seen several times is that the carbon of an epoxide is susceptible to attack by a nucleophile. Well, what are some other nucleophiles that might be useful in order to cause these reactions to occur? And one of them is alcoholates. So let's take an example of this. So an alcoholate is also a base. It's just not OH, it's O carbons, right? So if we take ethanol, CH3, CH2, OH, in the presence of minus O, CH2, CH3, okay, this deprotonated alcohol, now this is the base. So this is very similar to using water and OH minus, except we're using the O minus of the alcohol here. This can then attack. This can break. What do we end up with? Well, in this case, I'm going to give this some labels. So this is a CH3, this is an H, this is an H, this is an H. So we have the primary and we have the secondary. So if you remember, between primary and secondary, the major product is going to be with the attack at the primary carbon. So what we end up with is a C bonded to an OH now, because this bond breaks and then it gets protonated in the subsequent step, bonded to a CH3, bonded to an H, bonded to a C with two H's, and now this is attached, OCH2, CH3. So we end up with an ether and an alcohol when we attack with the ethoxide. So what we need to be aware of is which side the attack is going to occur on. And in this case, between primary and secondary, we get a predominant product of the primary attack, as we talked about before. So let's look at another type of nucleophile that we're looking at, and this one is a Grignard. So in this case, we have a simpler epoxide with just H's on both sides, so it's symmetrical. It doesn't matter which side the attack occurs on. And we add R, MgBr. All right, and if you remember, usually the Grignard is in ether, and then in step 2, we have to add H3O plus to protonate the alcohol that is formed, the negatively charged O on the carbon. So what's going to happen? Well, this RMGBr bond is negatively charged. It comes in, kicks this out, and what we end up with is a C bond OH, because it will get protonated by the H3O plus, as I just mentioned. Bond H, and then we have a C bonded to an H, an H, and an R. So we can make a bigger alcohol using an epoxide. So essentially, we turn this epoxide into a longer alcohol because this R, it could be a phenyl ring or it could be a carbon chain. It makes this a carbon-carbon bond, which is one of the very strong uses of the Grignard reactants. So basically, the idea here is when we look at the base chemistry of these epoxides, they're susceptible to attack where the base is acting as a nucleophile. Well, we use different bases, deprotonated alcohols and Grignards. Okay, we don't really think of Grignards as bases. We think of them as nucleophiles, but you get the same idea. And they can attack and cause these types of bonds. So in this last section, what I want to look at is a couple of examples where we predict the major product of a reaction. So we want to predict the major products of this reaction. We have CH3, bond C, bond O, bond H, bond C, bond H, bond H, and we add HCl and ether. Okay, and we want to see what's going to happen with this reaction. Well, in this case, we're going to end up with an alcohol on one side and a Cl on the other side. We have to decide which side the Cl goes to. If you remember before, we have a secondary versus a primary. When we have a primary versus a secondary, we most strongly favor the primary one being formed with the Cl. So essentially what happens here is we get protonation, and then the Cl minus comes in and attacks the primary one. And when we do that, we get CH3, bond C, bond OH after that bond breaks, bond H, bond C, bond H, bond H, bond Cl. Now in the next one, let's look at an example where we have a primary and a tertiary reacting with a large Grignard. So here we have CH3, bond C, bond CH3, bond O, bond C, bond H, and our Grignard here is phenyl magnesium bromide. So it's a fairly large Grignard reagent. We add ether and we add H3O plus. Now, how are we going to decide which side it goes to? We have a tertiary carbon here and a primary carbon here. Now, in this case, because this is a fairly bulky molecule, the attack of this onto the primary carbon is going to be more substantial than onto the tertiary carbon and the carbocation type of intermediate. So in this case, what we're looking at is the primary attack being right there. So what we end up with is CH3, bond C, bond CH3, bond OH, bond C, bond H, and we get that benzene ring attached, or we make the carbon-carbon bond, and we make this longer alcohol here would be favored because of how bulky this is. Now on a test, I wouldn't ask you something like this because it's kind of close. And I talked about before how this one was kind of mixed results. But this kind of thing would be more fair game. At the end of the day, what you really need to know is that when these epoxides are hit with alcohols or acids, okay, you're going to have something acting as a nucleophile. So if you have a halo acid, okay, like this one, this will be your nucleophile. If you just have an acid in water, the water will be your nucleophile. It starts by protonating the epoxide and then attack by the nucleophile. If you add a base like OH minus, the OH minus will attack, and then you'll get an O minus, and then it will be subsequently protonated. Also, we can add other types of things that we don't always think of bases. We more think of them as nucleophiles. Things like Grignard reagents and alkoxides, deprotonated alcohols. So hopefully this gives you a general idea of the reactions of epoxides, which can be very useful, especially in the case of the Grignard, because we can make carbon-carbon bonds and we can make larger alcohols in this way.